Hello, welcome to MEERTALK. My name is Kaeza Fern, and I'm the Director of Communications at MEER. We're really happy to get together for another MEERTALK today, and I'd love to begin by inviting everybody to turn your attention inward and take a breath and call up the reason that you're here. You might be just starting out to learn about this topic, or you might want to know more details about it. You might be really familiar with the topic already. But let's all connect with the larger reason for being here, which is most likely that we all are deeply concerned about the health of our beautiful planet that supports life. And for a moment, we can tune in and hold gratitude for that very thread of life that is running through. Today, we will be hearing from our guest speaker, Michael Diamond, postdoctoral visiting fellow at NOAA's Chemical Studies Laboratory. Then we will have a question and discussion period with three of our student researchers, Casey Goldberg, Alfredo Quesada, and Sophia Yue. In the final section, we'd love to hear your own questions, and we'll get started. I'm going to tell you a bit about Michael Diamond. Michael Diamond earned his PhD in atmospheric sciences from the University of Washington, Seattle, and is currently a Cooperative Institute for Research in Environmental Sciences postdoctoral visiting fellow at the University of Colorado Boulder and NOAA's Chemical Sciences Laboratory, and will be joining Florida State University as an assistant professor next spring. His research focuses on how the interactions between clouds and pollution particles affect Earth's climate. And if anyone has any questions that come up while Michael is presenting, you can send them along to Casey Rose Goldberg. Casey will be fielding the questions today. Okay, Michael, well, I want to congratulate you on your appointment to Florida State University, and you can take it away. So glad to have you.
So yeah, thank you for that really nice introduction. As a case I mentioned, I'm Michael Diamond. I have a ridiculously long affiliation, but I work at both the University of Colorado Boulder and NOAA Chemical Sciences Laboratory on understanding how clouds affect climate change, essentially. And for this talk today, I'm going to be talking about this idea called marine cloud brightening and asking the question, is it feasible? And I'm going to introduce a framework for thinking about how we might start to answer that question, which is called these checkpoints and exit ramps. And I'll explain exactly what I mean by both of those. And I do just want to mention from the outset, I'll be talking mostly on the physical science side. So thinking about the feasibility question in terms of if we wanted to brighten these marine clouds, could we? Which is related to but distinct from the question, if we could do it, should we do it? Which I won't touch on directly, at least in these slides. So I really like to start in conversations about climate intervention with job number one, which is mitigation, or the stopping to put CO2 and other greenhouse gases in the atmosphere. And there's good news and bad news on this front. So I'll start with the good news is that we are a lot better off than maybe we would have thought back in 2010 or back in the early 2000s. We were on track without any new policies for something like 4 or 5, even 6 degrees Celsius of warming by the end of the century, which would be absolutely catastrophic. The good news is that current modeling based on current policies has us more in the range of 3 degrees Celsius. So if you know much about climate change, you know that is very, very weak good news. 3 degrees Celsius is still a really bad place to be, but it's a lot better than 6 or 5 or even 4. So we've made progress. And if we continue having policies put in place by governments and corporations and other players around the world, we could get even closer and closer and closer to the Paris Agreement's goals of 2 degrees Celsius or 1.5 degrees Celsius. However, again, part of that bad news, our current policies are insufficient, and the policies we would need to actually limit warming to 1.5 degrees Celsius will be really, really difficult to put in place. And in the latest Intergovernmental Panel on Climate Change report, there are no model scenarios in which we get to 1.5 degrees Celsius without overshooting and having to go back down to that policy without relying on gigatons upon gigatons of carbon dioxide removal, so taking carbon out of the atmosphere. And we don't yet know if that's possible. So that's why we start talking about these things called solar climate interventions. And this is basically, can we reflect more sunlight and cool Earth for a temporary period of time and buy ourselves more time to have mitigation and carbon dioxide removal scale up to the level we need? So this is kind of a schematic right here of what that looks like. This red curve is where we would be at without any policies at all. So that would be huge, huge climate damages. Again, the most important thing we do is cut emissions. That would bring CO2 down, bring temperatures down. But there is a question of how fast we could do that. So to further limit climate impacts, again, we could do carbon dioxide removal, but right now we don't have carbon dioxide removal at scale. There's a lot of really fascinating, important work going into getting to that point, but we don't have it right now. And then this question here is, can we kind of shave this peak? Can we implement a temporary cooling measure and buy ourselves time to stay at 1.5 degrees Celsius or 2 degrees Celsius or whatever temperature target we decide that we land on? That's now been receiving some pretty high level attention from the United States government. This is a schematic from a report by the National Academies of Sciences, Engineering, and Medicine that was released last spring, looking at and recommending a US government program in studying whether or not these solar climate interventions would be feasible. So previous MEERTALKs have talked about stratospheric aerosol injection, so putting aerosol up in the stratosphere and reflecting light that way. I'll talk today about this proposal down here, which is brightening marine clouds. These are relatively low in the atmosphere from the surface to about 3 kilometers. So the first question I want to ask is, why focus on clouds, and why in particular focus on these marine low clouds? And it's because clouds have a huge effect on the climate. So in these top 2 maps here, the blue colors here show where clouds are reflecting a lot of sunlight and cooling the climate by preventing that sunlight from being absorbed in the Earth system. Clouds also warm the climate though. So these red colors here, where clouds warm the climate, essentially they act the same way as greenhouse gases. They prevent heat energy from the Earth from escaping out to space. So trapping that heat in the Earth system and warming things up. On net, that cooling effect wins out, and globally average, it's about -20 watts per meter squared, or watts per meter squared here is our unit that we use to think about heating or cooling from the energy perspective. And as a useful little ruler to have in the back of your mind, 4 watts per meter squared is how much warming there would be from an instantaneous doubling of CO2 in the atmosphere. So clouds in the natural environment are really important. That's 5 times a doubling of CO2. So as you can imagine, anything that changes these clouds, even a little bit, could have a pretty big lever on the climate. And when we're thinking about what types of clouds is generating that net cloud rate of effect, so the net cooling, it's mostly these low altitude clouds. So they're the vast majority of the effect because they're relatively bright and they're also relatively close to Earth's surface, which means their greenhouse effect is small. So that's great, but can these clouds actually reflect any more? Are they kind of already saturated? They're reflecting all they can reflect. And we have a couple of ways to know that that's not necessarily the case. And part of that is through these things called ship tracks. So this satellite image here is one of my favorite images. It's a super cool image back from the 1960s. The first time we picked out these things called ship tracks in satellite pictures. So these little lines of brighter clouds that you could see here in a more modern picture taken from the International Space Station over on the sidebar. These follow individual ships and are caused by the pollution being spewed out from the ship smokestack. And we can actually observe a substantial brightening of those clouds that are following the ships. And all the way back in the 1960s, when this was first identified in the in the literature, there's actually this amazing paper, and there's this paragraph at the end of that paper proposing that because we saw this inadvertent brightening in the ships, it should be possible to do it deliberately if we so chose. So this idea actually is extremely old, but it was revived in the context of fighting climate change back in 1990, and then really experienced more and more interest over the last decade and a half or so. So how does this work? So if you're out over the remote ocean, all clouds need to have some kind of basically a seed, or what we call a cloud condensation nuclei. So some aerosol particles, so just some particle in the atmosphere upon which water vapor can condense and form a cloud. So out over the remote ocean, the only things you have in the atmosphere that can do that are some salt particles kicked up by the wind. So now imagine your ship goes by, or the winds shift and you start getting air from the continents coming in, and has a lot of these little pollution particles, these little aerosol particles coming through. Now, instead of building a cloud with a relatively small number of large droplets, you could build a cloud with a relatively large number of small droplets. That increases the reflectivity of the cloud, which means more sunlight is going back out to space, less of it's being absorbed in the earth, and that's a cooling effect. And this is what happens if you have the same amount of liquid with which to build your cloud. But that obviously isn't always the case. So on the side of increasing brightening even further, we have an effect called drizzle suppression. So if you have these clouds that are naturally precipitating and your ship comes by, these cloud droplets that precipitate, to coalesce together, they need to be relatively large. So if you have a bunch of little droplets, they're not good at precipitating out, which means that cloud's not going to lose that liquid, which means it could potentially become thicker and stay in the atmosphere for longer. On the other hand, these small droplets, especially when they're near cloud top, evaporate a lot easier, which can cause more entrainment, which is kind of a fancy way of saying mixing in of warm, dry air from above the cloud down into that cloudy layer, which will evaporate the cloud away. So this would be a cooling effect in the drizzle suppression that enhances the Toomey effect, or you could have a drying effect that counteracts the Toomey effect, which is part of why this is so uncertain. So because we have these uncertainties, we need a research roadmap to think about how do we figure out whether or not overall we can actually successfully brighten marine clouds to temporarily counteract some effects of global warming. So this schematic here is our research roadmap for how we're thinking about this, involving these 6 checkpoints, where here we're defining these checkpoints as relatively self-contained topical areas where we have these big open questions to determine whether or not this could be feasible, and exit ramps. So thinking about what could we find that would tell us marine cloud brightening isn't feasible, and we therefore don't need to continue research, and we can shut down this research program. So these 6 checkpoints that we identify, I'll go through each of them in a little bit more detail later on in the talk, but briefly now, you have to be able to generate these particles and deliver them to the clouds. Once they're at the clouds, these cloud adjustments, like that entrainment effect I just talked about, can't substantially offset the brightening you would get from that Toomey effect. These clouds that actually are susceptible to brightening have to exist at the right scale and in the right location, so you have enough of a lever on climate to get the effect you want. You have to be able to detect this effect from space if you want to be able to change in response to new conditions or concerns. And you have to worry about unintended consequences and impacts, both locally on marine ecosystems and coastal communities, and globally in terms of potential circulation effects. So for a second, we're going to zoom in on this concept of exit ramp. So where is that coming from? Because that's a little bit harsh, right? So in the National Academy's recommendation, they specifically call out wanting these criteria and protocols for terminating research programs when it's found that a program would not be feasible. And this comes out of the social sciences literature, avoiding a concern called lock-in, or called the slippery slope, where if you start doing research on something, you might start generating stakeholders in the research community, maybe people who own patents on the technology, maybe just you have institutional inertia, and it starts going forward by its own momentum. And on the one hand, that could lead to wasteful or unnecessary research if it turns out it's not feasible. Or more concerningly, it could lead all the way to a deployment that wouldn't be warranted, either because it wouldn't work or because the side effects would be worse than the temporary cooling effect that you would actually get. So how do we kind of see this working? This is a idealized flow of information coming from physical sciences, technology, ecology, social sciences, and ethics, informing how we assess these technical feasibility checkpoints. And as long as all of these checkpoints pass, or at least until any of these fail, what you do is you do the research, you disseminate the policy relevant knowledge, and you loop back around and keep on testing hypotheses, et cetera. But if any checkpoint fails, that would be grounds for terminating the research program, because each of these, as we're envisioning them, are necessary conditions for this program to be feasible. And the same thing would exist on these social feasibility, so the should we questions, although I don't quite address that here. So let's go into a little bit more detail. What do we actually need to find, or what could we find that would be concerning in these checkpoints? So first of all, let's think about this generation and delivery. So it must be possible to generate and deliver to cloud base particles of the appropriate size. This video that I'm showing here is from a small field trial that took place off the Great Barrier Reef off the coast of Australia a few years ago. The video is from Southern Cross University. So we have these questions of, can we make these technologies that actually generate particles of the size we want? And then once we do, will they actually get lofted into the atmosphere, which we actually do see happening here? Or rather, will they kind of fall right back down into the ocean? Because as you're generating these salt particles, you're also evaporating water, which cools the air down and makes it negatively buoyant and fall. So you can actually see that starting from the boat here. It goes up at first, and it actually almost falls into the water, but then it gets lofted up. So in what conditions will it actually be lofted to the clouds and actually seed these cloud particles that we want? Once it does see those cloud particles, what's going to happen with those adjustments? And we'd be really concerned if those adjustments start substantially offsetting the microphysical brightening and precipitation suppression effects. And this little schematic here is based on a modeling study from Hoffman and Feingold that was published last year, where they found that if you have even just a few of these cloud seeds that are too large, instead of suppressing precipitation, you can actually enhance precipitation and seed these drizzle droplets that'll break up the cloud. Versus if you have too many of these particles and they're all too small, you'll get that evaporation effect on overdrive, and that will decrease the cloud cover you have to work with and the amount of cloud there, which would be a warming effect. So either of those ends, we kind of need to find the sweet spot for getting these adjustments that will brighten the cloud without having these warming side effects. Once we have that under a certain weather state, we need to see if that scales. So these clouds exist consistently at regional or global scales. So here in this figure, green dots here are areas that are have cloud brightening or inferred cloud brightening from satellites when you add aerosol. Brown areas where you have cloud darkening. And on the x-axis here, this is how many cloud droplets are there naturally, and on the y-axis, this is how much liquid water is in the cloud. And these different plots are showing for different sea surface temperatures, but you could do this with different weather states. And the point here is that where you have these areas of brightening and how often they occur really depends on what the clouds are doing in the natural background and also your weather state there. So you want to avoid these brown areas and hit these green areas. So we need to know this. This is for off the coast of California. We really need to know this globally to know what scale are we talking about. In terms of signal detection, we need to be able to detect these changes on a time scale that would allow for adjustments, new conditions, or concerns. In this study that I'm showing a plot from here, the blue and green dots here are from the South Pacific off the coast of Peru and the North Pacific off the coast of California. So two areas that would be prime target for these types of clouds. And what they found in this study is that you would need about a 10 to 20% increase in planetary albedo, which is relatively large. Albedo here being the technical term for how much light Earth reflects back to space. So you need about a 10 to 20% increase to detect a regional test of marine cloud brightening within a year. So it's relatively a large change you would need for that field trial to be able to know that it's doing what we want on that regional scale. Then, as I mentioned before, we need to worry about those local impacts. So marine ecosystems, we're changing things like the ratio of direct to diffuse sunlight that's getting to the ocean surface. So how will that change plankton and algae? Marine coastal communities. So will this salt kind of blow in and affect coastal infrastructure and marine chemical cycles? That's a picture of this here is how much ozone is there in the troposphere here. And here's actually kind of a good news finding is that by pumping more salt into the atmosphere and more iodine in particular, you actually might decrease ozone pollution in the lower atmosphere. So some of these marine chemical changes could actually be beneficial, but they need a lot more study to know whether those will be good or bad, and how concerned should we be about some of those chemical changes. And then finally, we're thinking about these remote impacts. So here, the risks of adverse circulation precipitation changes can't outweigh those from unmitigated warming. And one thing we know from these solar climate interventions is for the same cooling of climate, you're actually going to more strongly change precipitation. So if you were to offset all of the greenhouse gas warming with a solar climate intervention, you would definitely get a global decrease in precipitation. For marine cloud brightening, it's a little bit more complicated though, because you have these, this what we call heterogeneous spacing, or you have brightening in different splotches of the Earth. It's not uniform, right? So you can get these circulation changes. So here, this is a multi-model look at what happens if you brighten all the clouds over the ocean. What you get is that global drying effect, especially in some of the tropical areas here, but over tropical land areas that we might be concerned about, you actually get an increase in precipitation. So that's actually maybe again, maybe a good news thing for marine cloud brightening, but we know maybe seeding in certain decks, like off the coast of Africa here, might affect rainfall in the Amazon. We have to be really careful about those specific effects when we're thinking about this heterogeneous forcing. So where I kind of want to end before summing up is on the need for transdisciplinary research to attack many of these different questions. So I'm most comfortable here with the physical science, and the physical science touches on all of these. But we also need technology, especially when we're starting to think about the generation and delivery of these particles. So can we actually make these sprayers? Ecology, so I mentioned the Great Barrier Reef before. Do the clouds that we actually need to occur to get this brightening effect, will they occur over sensitive ecosystems like the Great Barrier Reef that we might want to save? And then social science and ethics, so especially for how is this going to affect ecosystems and communities, and how do we weigh these different impacts? We really need the ecology, social science, and ethics fields to be at the table to help us assess these questions. So for the large-scale circulation response in particular, where is precipitation going to change and by how much? It might be mostly a physical science question, but are those changes ecologically important, and how will that affect communities? We need more people at the table to be able to answer that. So I'll just wrap up with some key takeaways here. Marine cloud brightening is proposed as one possible strategy for temporarily limiting global warming to below 1.5 degrees Celsius. But we still need a lot more research to assess its technical, which is what I talked about today, and also its social feasibility. And our contribution here in this paper that I've been showing some figures from was kind of identifying those 6 key priorities on the physical science side, and also highlighting their transdisciplinary connections. And we believe that the identification acceptance of these exit ramps could help guard against lock-in. So we could help terminate an unnecessary research program if MCB is unfeasible, or especially unwarranted deployment if the risks of MCB wind up outweighing those of unmitigated warming. So with that, thank you so much for listening, and I look forward to taking questions.
Fantastic. Wonderful. Thank you, Michael. Yeah, we are going to bring on a few of our student researchers. Sophia Yu is currently researching how emission byproducts from chemical industries can be utilized to form useful nitrogen-based products at MEER. She recently graduated from Vanderbilt University, where she studied chemical engineering. Sophia also enjoys baking and ultimate frisbee. And Alfredo Quesada is studying the effects of changing environmental conditions on species across major trophic levels here at MEER. He is a marine biologist from the University of California at San Diego, and is currently working on a marine sciences degree at Nova Southeastern University, looking to further the research and conservation efforts of our ocean's megafauna. Casey Rose Goldberg is very excited to be working on social media outreach and literature review team member at MEER. She's extremely passionate about developing innovative and successful solutions for our broken planet's environment. And in the future, Casey aims to work in this field and in wildlife biology. So thank you all three for coming on today.
Hi, Michael. Thanks for your great talk. We all really enjoyed reading your paper and hearing you talk a little bit more about it. I'll kick off our first round of questions. So one of my questions was, what percentage of the ocean surface is suitable for this operation? And would you be able to provide an approximate reference area?
Yeah, so that's a fantastic question. I'll actually start by saying, go Doors. We have the same alma mater, so that's awesome. So yeah, that is a question that is currently the topic of a lot of research, because not only do we need to know where are these clouds occurring, but we need to know, are they occurring under these weather states that will actually allow for brightening, or will we accidentally get some darkening? But roughly, so these low altitude clouds cover about a quarter of the global oceans. And yeah, as I mentioned, so we know that that's where all those clouds are, but then what we need to know is, are they kind of occurring in the right weather states? So we know under some circumstances, so I'll take an example off the southwest coast of Africa. There's a major shipping corridor, and we can actually see in the satellite climatology that there's a statistically significant increase in the number of cloud droplets that form in that shipping corridor and the brightness of the clouds there. But we mostly see that for what we call the subtropical area. So that's an area where we have especially these even most shallow clouds, so around 1 kilometer in altitude. When you start getting more tropical and these somewhat deeper, what we call trade cumulus clouds, we actually are no longer able to get a statistical signal. So we don't know that they're not brightening there. It's just that it's a lot noisier. There's some research that I know will be coming out in the next several months that suggests maybe we are actually getting a big signal there, which is potentially exciting. But yeah, so it's a little hard to answer now, but the answer, if we can brighten everywhere, that would be great. But we know that there are some areas where either we'll get very little response, or we might even get a counteracting response.
Yeah, so going off of that, like in the idealized situation where we are able to brighten the whole area where marine clouds are, how much do we need to increase the cloud coverage or the brightness in order to actually see a sizable impact on the global temperature to keep it within like the 1.5 degrees Celsius as dictated by the Paris Agreement?
Yeah, so a lot of that will depend on where we're starting from. So if we're on something like what we call the RCP 8.5 scenario, which is like the one of the worst case fossil fuel burning scenarios, you would need a huge amount of forcing to get back down to 1.5 degrees Celsius. Versus if we're on something like we would be heading towards 2 degrees Celsius and we just need to bend the curve down to 1.5, you would need a lot less. My old PhD advisor, Robert Wood, has a nice paper on this recently, only looking at the Toomey effect, but he calculated that you could actually offset a doubling of CO2 theoretically if you used basically all of the low clouds over the ocean. How much salt you would need to spray depends on a couple of assumptions about the size of the salt particles. But yeah, I'm trying to remember exactly. Off the top of my head, I don't remember what percentage increase in cloud droplet he needs. I will say also that depends a little bit on the background state as well. So if you have these really pristine areas where you have, let's say, only 40 droplets per cubic centimeter in the air, doubling that requires a lot less salt spraying, right, than somewhere where you're already off the coast of California and it's pretty polluted, and maybe you have 100 to 200 and you're trying to get to 400.
Cool, thank you. So my next part is moving on to signal detection, which was one of the major categories that you talked about in the plan. And you already touched on the albedo timeline of measuring throughout global variations when it comes to that. So my question is more focused on, are we able to get a measurable signal with these small test projects like the video that you showed to detect global average temperatures? And how many years would it really take for continuous data collection to see such a signal in changes in global temperatures due to MCV?
Yeah, that's a really fantastic question. And when I'm thinking about these field tests, there's a really sharp scale break in what we can do. So these very small scale tests, like off the coast of Australia right now, which actually haven't even gone on to look at the cloud effects, only thinking about the generation right now. And then maybe a future test where we're doing something like generating a salt track, kind of like a ship track, and maybe doing a couple of those. There's basically no way you would detect temperature effect from those. You probably would detect them from space in terms of cloud brightness on that day. You would be able to see them like you would a ship track under the right conditions. But if we're starting to think about kind of like that figure I showed, where like, what if you're doing it for 1 year with a 10 to 20% increase in albedo? We'll be able to detect the brightness change probably before the temperature change. There's so much internal weather noise or natural variability in the climate system. It would be really hard to detect this on less than a couple of year timescale unless you're doing a really big effect. So something like the Mount Pinatubo eruption in the early 1990s, that was, I think, about a ½ degree of cooling that you could detect within a year. But that's pretty extreme. We probably wouldn't want to do a regional experiment that was quite like that, or you would basically just be deploying at that point. So it's actually a huge question. I mean, one thing I'll say is that there currently is research into this and continuing research using what we call large ensemble initial condition climate models that will be able to answer this question of looking at different kind of states of weather noise where you're starting. How long will it take you to detect something like global average temperature, but then maybe more importantly, how long would it take you to detect a precipitation change in the Amazon or one of these other side effects? And my guess is that when that research is done, we're going to find that it's probably going to be on the order of years for all of these things, just because there's so much weather noise. Hopefully I'm wrong, so it'd be really convenient if we can find some good statistical metrics that would be able to detect it faster. And there's some fancy things we could potentially do with that. But the way we are able to detect things now is a little bit more pessimistic on how fast we can do it.
Okay, cool. Yeah, hopefully once the studies get started, that we can be a bit more optimistic with the time scale for data collection with global temperatures. I have one last question before I pass it off to Alfredo. So in the case that different national programs find conflicting results for each checkpoint, who would make the last call regarding the project status, as there will be some winners and losers when it comes to that regard?
Yeah, that's a really fantastic question. And hopefully, eventually, there actually is an international research program that gets spun up that would have set procedures for that. The way we're envisioning this now is that it would be, and we kind of are focusing mostly on the US case because myself and all the co-authors who worked on this paper are US-based scientists, and we were kind of going off of that US National Academies report, but I think it's applicable to any other country who would want to pick it up. So the way I'm thinking about it now is that if we imagine in 5 years from now, the Global Change Research Program or some other program has spun up a national US program, there could be some kind of committee of not just scientists, but also other stakeholders that would assess this. As a physical scientist, I'm not sure I can go into too much more detail about exactly how that would work. You would need a lot of governance scholars helping to figure out how to make that happen. But yeah, I think, yeah, it's going to be really thorny, actually, how you decide how to take one. And one thing I would caution against is you need a very high evidentiary standard to take an exit ramp. It can't just be one group came out with one study suggesting this could be a bad idea. You really need to kick the tires and make sure that that's not just in one model or in one deployment scenario, but rather there is no plausible way forward, which would require a lot more essentially community consensus around it.
Thank you for answering my questions, Michael. That was very helpful. I'll pass it off to Alfredo now.
Sorry. Hey, Michael. Again, thank you for your presentation. My questions are more ecologically inclined.
Mhm.
So to start off, we know that clouds move over pretty large distances, probably in the tens and
Mhm.
to hundreds of kilometers throughout their lifetime. And we also know that ecosystems that are separated by these distances experience very different background weather or environmental conditions. To your knowledge, is there any current strategy within the marine cloud brightening research community regarding setting up ecological impact studies with rigorous background control measurements to test for these effects?
Oh, good question. Yes to the first part. Are there going to be studies to test for this? Rigorous background conditions is maybe something I have to hedge about a little bit, especially because that would probably matter most for these field tasks. If we're thinking about in a climate model world or ecological model world, you could have a rigorous background in a way that is a little harder to set up in the real world in terms of how you would actually observe everything. I am currently involved in an effort to think about how marine cloud brightening or stratospheric aerosol ejection will affect global shipping. Not shipping, global fishing. Also on shipping, but that's a little less relevant to your question. So it would be an intercomparison of fishing models to look at how that might affect different things in terms of catch and ocean productivity, et cetera. There is, yeah, so that type of work is starting now. I think it's relatively, I'd say maybe a little bit behind some of the other physical sciences work. In terms of the field testing, I think it's really tough because at the point at which you actually get something that's going to say, we're seeding off the coast of Peru, and maybe that'll have downstream effects on mountainous ecosystems in Costa Rica, it gets really hard to pick those out, especially if you have a small field test. And then even if you have a large field test, I think it would take quite a bit of time to pick that apart. So I think, how do we design experiments where we can test for some of these side effects and get enough confidence in them is going to be really a good challenge. So it's good that you have smart folks like you who are going to be working on the ecological side to help us out with this. But I think this also gets to one thing, is that we are just realistically going to be making some decisions under deep uncertainty. We're never going to be able to do enough studies to resolve all possible scenarios or all possible impacts. And this is true both for how will unmitigated global warming affect these ecosystems, and how would some deployment of climate intervention to offset that warming will affect them. So I think the answer is going to be a little bit, we're never going to have exactly the data we're going to want to answer this question, but it's kind of, how do we get closer and closer to what we need?
All right, thank you very much. For my second question, it's a little bit inspired by your answer to Sophia's first question. If marine cloud brightening deployment is to be localized to a few key regions where you know it's gonna have an overall effect, what changes would we expect to see in primary productivity levels of either terrestrial or marine environments with a significant and uniform local reduction in available sunlight?
Yeah, that's a really important question, a really uncertain one. So you could, I guess as a first pass, you could imagine that you're decreasing the available sunlight, so you'll get a decrease in primary productivity. But of course, biology is not quite that simple. We already don't know that the communities that are living in some certain area actually have the ideal amount of sunlight. They might actually not be affected that much by, say, a 10% reduction in sunlight. But more importantly, they might actually be more affected by the ratio of diffuse to direct sunlight. So we know from some studies of volcanic impacts and stratospheric aerosol injection on when we start putting those in crop models, et cetera, some vegetation actually responds better to the increase in the diffuse amount of light that they're getting, and don't actually care as much that they're getting a little bit less overall light than they were before. So will that scale to the ocean is, I think, a really good question. That's probably something where we actually need to think about these specific areas. So are the phytoplankton in the Benguela upwelling region going to respond similarly to those off the coast of California? could be a good question, where I'd imagine they're probably similar, filling similar ecological niches, but that's something that I think needs to be studied.
My last question is pretty much divided into two parts. So for the first part, given the short lifespan of clouds, the condensation nuclei need to be continuously replenished for marine cloud brightening. So how feasible is it from a marine fuel consumption point of view to replenish these particles every 3 to 4 days whenever the clouds die off on such vast regional areas?
Yeah, that's a really great question. That'll get to engineering challenges, which I know folks are working on. I probably can't speak super informed on this because I'm not an engineer myself, but I think a lot of this will come down to what kind of delivery systems do we have, and are these delivery systems able to work on something like local solar or wind power or tidal power or something like that, or are we going to be burning fossil fuels to get these ships out there? And hopefully it would be the former. So again, this kind of gets into this point of climate intervention really only makes sense as a complement to mitigation, not as an alternative to mitigation. So we need to be moving forward on these cleaner fuels for all forms of transportation anyway. So hopefully marine cloud brightening is able to jump on that bandwagon and also use cleaner fuels, in which case that would be less of a concern. A little bit related to that, there's actually in the literature one paper that suggests you take the current ships that burn this really dirty bunker fuel. We actually just had a regulation go into place that decreased the amount of sulfur that's allowed to be in them, and sulfur makes really good cloud seeds. So there's one paper looking at, well, what if you only burned this really dirty fuel out over the remote oceans and burned the cleaner stuff closer to shore? Can you capture the health effects but still get some of the climate effects? And it seems like maybe, probably not the best idea, but there are folks who have thought about that. So I'll punt a little bit, but say that my impression would be that if we're at the stage where we would be deploying this, we would first go to something where you could actually try to generate the power these ships would need from the local environment, at which point that question, if we can solve that engineering challenge, I think we have to worry a lot less about fuel costs and also just fuel contributing to greenhouse gases.
Yeah, actually, my second part of the question was on this topic of fuel. If the vessels required that would spread these particles to ensure the productivity of marine cloud brightening, if they were to use fossil fuels, could the cumulative CO2 emissions from operating of these vessels eventually cancel out the temporary cooling that marine cloud brightening could provide?
The answer is probably geophysically yes, if you did it for like thousands of years. But like, let's say if you're at the point where you're getting like that much fuel burning. So right now the global shipping is a couple % of global CO2 emissions. So let's say you're just basically doubling that to get if you double that, maybe you have something like an offsetting of a doubling of CO2. So that's about 4 watts per meter squared. That's what was in that Robert Wood paper I talked about earlier, where I think he estimates you need something like 10% to 100% of the current fleet to do this. If you, let's say you mitigated absolutely everything else and just got that cooling effect, you would be able to go off of that for quite some time, as I guess a hypothetical. But yeah, I think my answer to that mostly is if you are able to get a strong cooling effect, you probably don't need to worry too much about the direct CO2 emissions, assuming that's like the only thing that's left. But that's probably not the most useful hypothetical, because if you imagine you're still using fossil fuels to run these ships, you're probably still using fossil fuels generally in the global economy. And then you have this problem that you're probably on one of these high emission scenarios. Sorry, in the back of my mind, I'm bringing in something else I didn't actually introduce, so I should probably mention that. There's also this question of what we call termination shock. So if you were to suddenly stop doing seeding, both in terms of the stratosphere or in terms of marine cloud brightening, If you suddenly stopped, you would unmask all of that warming. We're seeing actually a version of that right now where pollution levels actually have started to go down globally since the 2010s, and that might actually be accelerating warming right now. So essentially, you don't want to wind up in a situation where you're offsetting too much greenhouse gas warming with a solar climate intervention, because the risk of that termination shock increases with the kind of delta between where you would be on the greenhouse gas world and where you are in the solar climate intervention world. So it's probably, yeah, like you don't want to find yourself in a situation where you're offsetting a full doubling of CO2 and also doubling the CO2. You definitely don't want to do that.
All right. Thank you very much, Michael. It's been really nice talking to you. And I'll pass it on to Casey now.
Hi, thank you so much for answering Alfredo and Sophia's questions with so much grace and knowledge. My questions are a little more geared towards policy, and I know that's not your area of expertise, but it does blend a little bit of physical science. So my first question is, at the June MEERTALK this year, Leon Simons presented about significant global cooling from those sulfur emissions in international shipping that you were just talking about with Alfredo. And he also showed evidence for global warming following recent clean air policies. So reverting back to high sulfur marine fuel to cool Earth seems ready without any additional investment in R&D. And knowing that you've done research in the past regarding shipping, how do all of those economic, energetic, social, material, and ecological metrics of undertaking new research in marine cloud brightening compare against just immediate policy relaxation of sulfur content?
Yeah, that's a really fantastic question. And it brings in another side of the science of changes in our atmosphere, which is air quality. So at the same time that these pollution particles have been cooling Earth, they've also been sickening us. And essentially, every time someone does a study on pollution in the air, we basically just find out it's worse than we thought. It almost never goes the other way, where we realize, oh, actually, sulfur is fine. Yeah, breathe as much of it as you want. So I think this gets back to what are we trying to do? And we often talk in terms of temperature targets, but really we're talking about impacts targets, right? Like what we want is a safe climate. What we want to minimize is our climate and environmental damages. So when you start talking in that frame, I think the proposals to maybe delay those IMO regulations or potentially burn more sulfur even far afield become less appealing, just because we know that air quality impacts are so bad, especially for the coastal communities that would have to breathe this air. And actually, when you do a lot of the economic modeling of climate change policies, a lot of the actual benefits of the climate policies aren't even just from averting climate change, they're from cleaning up the air. So I would say it's a little bit of a Faustian bargain to take more air pollution now in exchange for a little bit less climate change in the future. I think it's more important to tackle both of them simultaneously, because what we care about at the end of the day is reducing impacts on human health and on ecosystems.
Thank you. So question 2 is that whenever there's a disturbance in the natural world because of experiments or anything of that sort, it often requires a period of acclimation before you can really extrapolate long-term impacts. So in comparing the potential effects of solar radiation management, like marine cloud brightening, aerosol injections, to unmitigated warming, what's your opinion on the deployment timeframe that we should be using?
Oh, that's a really interesting question. Like in terms of how quickly do you ramp something up? Like yeah, so you don't want to just like put a hammer to the system. And
exactly.
I mean, that's what we do in models, right? We want to have a hammer to the system and see how big things change. But in reality, we want to have like a glide path. Yeah, that's really interesting. So I'd say probably in a scenario, like let's say you're trending towards a 2°C world and want to keep it at a 1.5°C world, that's a scenario in which you probably could do that glide path a little bit more feasibly, where you essentially ramp up your deployment, not so that you're necessarily getting cooling in any one year, maybe just small cooling in one year, but essentially limiting the rate of warming. So that would be, I think, a good use case for a solar climate intervention. One thing that we think about in the ecological impacts is something called climate velocity. So basically, how quickly are things like climate and precipitation changing, and how quickly can ecosystems basically adapt to those changes by through migration or through other forms of adaptation. And that's, yeah, as I mentioned before with that termination shock, one of the big concerns about termination shock is you really ramp up that climate velocity. So basically, if you could use a climate intervention to essentially get that climate velocity down to 0, that's what you would want to do. And of course, if you have one global target, it's going to not be the exact same everywhere regionally, right? Some regions will still warm faster and some will warm cooler. So you probably want to try to maximize not just for a global average, but where do you have vulnerable ecosystems or something that you're trying to save. But yeah, so it depends a lot on what the deployment strategy is. But I think if you are in that peak shaving world, it does seem like it would be plausibly feasible that you could limit the climate velocity that way. Because yeah, what you wouldn't want to do is like tomorrow be like, oh, we're going to go back to pre-industrial, like flip the switch. That would probably cause some issues.
Awesome. And then my final question is, since humanity's struggling with limited time and resources in terms of the climate crisis right now, we don't want to get locked into inadequate and potentially dangerous concepts just because it's the first one that we have. So what is your opinion on establishing an overarching global research framework in climate cooling technology that has a mechanism for quickly integrating new concepts as they emerge, kind of like the IPCC report, but with more focus on technological engineering and experimental ecology?
Yeah, I think that would be awesome. I don't know how one goes about setting it up. I know that climate intervention research has been brought up at different UN level bodies briefly. There was a failed effort to have it be addressed by the United Nations Environment Program a few years ago. I think it might be coming back to some of those forums. There are some more informal forums right now, like the Overshoot Commission that's looking at that. But it's something that in the National Academy's report, and I think this is probably what's most likely, they lay out an argument that what's really going to happen is you're going to start with these national research bodies, and that's going to build up into an international research body. It's probably unlikely that an international research body will be stood up as the very first thing. It would be great if that's wrong and we could actually get some cool international research going on, but it doesn't necessarily seem the most realistic to have that spin up on the time scale of international governments. I think is slower than the time scale we need to be starting research right now, unfortunately.
Great. And just as a quick follow-up to that, if we were to create a more global framework for not just marine cloud brightening, but any climate intervention, what checkpoints do you think would be necessary to add that could be more general?
Oh, interesting. Yeah, so we tried to design at least the physical science checkpoints in mind for global consideration. So I'm not sure that we would necessarily need to add a checkpoint, but I think that one checkpoint we would need to go in more detail on is that scale of susceptible clouds. So in the paper, we do have a couple of lines about how that checkpoint kind of serves two purposes. The first one is thinking about for a global climate intervention. So kind of what I mentioned before, like going from a 2 degree to a 1 degree world. But you also have these regional applications. So like the Great Barrier Reef, can you, even if it's not feasible to do it globally, can you feasibly do it to protect the Great Barrier Reef? Or can you feasibly do it to, I don't know, protect some cloud forests in Costa Rica if you're just seeding some areas off of Peru or something like that? So that type of thing I think would really benefit from a more global approach, because different areas are going to have different things that they would care about in terms of their local ecosystems. And one thing that'll be important thinking about that is how will those regional, so one thing that we know in climate is what happens in one place doesn't stay in one place. So how would those regional applications interact with each other, I think would be quite important.
Thank you so much. That's all the questions the three of us have for you.
Awesome. Thank you so much for the excellent questions.
All right. Thank you all for asking all of that. And we are now going to open it up to hear from all of you. So we invite you to write any more questions into the chat. I know there have been some questions already coming in. you can put them to Casey Rose Goldberg. And please do try to be brief and to the point, and we'll collect your questions and cover as much material as we can here. So first off, here's a question from Leon, fairly scientific, so I hope I speak it okay. Is the estimated needed albedo increase regional or global? And is the albedo increase of 20% relative to the current albedo? And then there are some parentheses with the current albedo of around 30%, 1.2 is 36%, or absolute in percentage point albedo of around 50%.
Yeah, it was relative albedo. I would probably refer you to that paper, which is from Nature Climate Change in 2014 by Diane Seidel and colleagues for the exact details there, because I probably won't remember them off the top of my head. But yeah, so that what they were looking at is basically if you had a 1 year uniform perturbation in albedo based on detecting it above interannual variability, what would you need? And for that, the albedo change there you need is something like 0.03 or 4. Sorry, I calculated this earlier for the purpose of bringing it up there. But yeah, it's like a relative albedo increase of between 10 and 20%. You can kind of take different parts on the graph and get something as low as like 14% and as high as a little over 20% from that one figure. I wouldn't take that, again, I wouldn't take that super duper seriously. It's a little bit of just a thought experiment, but the main point there is you need a relatively large signal for detection on an annual time frame. And along those lines, so thinking about the Southeast Atlantic shipping corridor that I brought up before, you only need about a year to detect that the brightening effect is different from zero. Sorry, that's not quite true. That you only need about a year to detect that the microphysics effect, so the impact that having greater numbers of cloud droplets is different from zero. But you need about 5 to get the magnitude nailed down. And you need 3 to 6 years to actually be able to detect the brightening effect. So that would be basically, so you can imagine if you were recreating the brightening from the corridor or something like that using the same statistical methods, again, you would need a relatively long lasting field campaign. Again, you could hit it with a harder hammer. The harder you hit the system, the more detectable it'll be, but that's getting into questions of, will you start having side effects? And then I've been talking with a couple of folks on the kind of radiative transfer side of things about, can you do interesting things like start making detections in like a sine wave pattern, or do other things with signal detection where you just make a really unphysical or unnatural cadence necessary or something like that to the forcing, and can you do a faster detection there if you kind of know the frequency you're looking for? So that's some research that might spin up. There's also the question, can we use something like machine learning or transport models going from each individual salt spray or each individual ship that we use to scale from the bottom up the albedo change rather than kind of looking from the top down. And that might also get us faster detection, but that requires more research. And also would be a little bit more susceptible to something like if you have some regional circulation change where you get brightening right in the salt track, but you get some kind of darkening at the edges. You wouldn't necessarily be able to detect that if you're just looking at the salt tracks.
Okay, great. So I imagine this next question you kind of addressed in what you just answered, because Neil asked about, wouldn't top of atmosphere energy balance be a more direct measure with an earlier signal than surface temperature? And it sounds like you just kind of were referring to some of that.
Yes, surface temperature will be very difficult to detect, especially for a regional task. So that's one more, one more thing removed from what we're actually doing. And there's just also a lot of natural variability. So you need to care about if you're an El Nino year or a La Nina year, and also these decadal sources of variability. So yeah, detecting temperature change of a regional test would be extremely difficult. But again, if you know the spatial pattern you're looking for, that might aid in detection. So if you run the regional test in a bunch of different climate models and they all suggest the same kind of regional pattern, like I'm going to completely make this up, but let's say you get more cooling over South America and more warming over Europe because of some dynamical adjustment. And you are able to, maybe if you know you're looking for that pattern, you might be able to detect it out of the observations if you are able to subtract out El Nino and stuff like that. So there's some chance that we could use more advanced spatial statistics if we know what we're looking for to get at faster detection. But I would be very pleasantly surprised if we can get detection down to the annual to subannual timescale.
Got it. Okay. Alex is asking, what model or models and lateral grid spacings were used to create the precipitation impacts figure?
Oh, good question. I'll also probably refer you to that paper in particular by Camilla Stern in Atmospheric Chemistry and Physics from 2018 for the exact details. I think there were 6 models that participated in that experiment from something called the Geoengineering Model Intercomparison Project. And that was the experiment where they uniformly increased cloud droplet concentrations over the ocean by 50%. I'm pretty sure at least the Norwegian and UK Met Office models are in there, but I can't remember exactly which models did which experiments off the top of my head. That isn't the only one that has been used, so I don't think it participated in that intercomparison, but NOAA Geophysical Fluid Dynamics Laboratory has done some studies with their climate model in a slightly different configuration. The UK Met Office has actually done a few different configurations with a few different versions of their models. So yeah, it would be nice to get more. I think if you look at all the models participating in CMIP 6, there's something like 50. So the fact that we only have 6 in that in comparison means there's a lot of room for improvement. But quite a few different modeling groups around the world have at least started to look at this.
Okay, next question is from Rebecca. Is there a mechanism to burn off clouds if it gets too cold?
Oh, interesting. So like purposefully going for the negative adjustments. I think the simpler way would be to just seed less. So instead of, so let's say you're, I don't know, doubling the cloud seeds available in a certain region, and actually you find out you're overcooling. Instead of doubling, you could just go down to increasing by 1.5 or something like that. I don't think you'd want to get into the point at which, like, I don't know, you're releasing hydrofluorocarbons to get some warming in certain places and then doing marine cloud brightening and then also adding a little bit of stratospheric aerosol injection to undo some of that. That's probably starts getting, I think there's probably more room for error there. I think you'd probably want to have the lightest touch possible. So rather than having an offsetting warming, you probably just want to do less of the cooling.
Right, that makes sense. Okay, we have a question from Mark at MEER, and this is a little longer, but I'm gonna just read this out. His question concerns what he fears and what appears already to be the overweighting of the opinions from people responsible for analyzing mitigation strategies who would fall under the social sciences group, such as psychologists, sociologists, philosophers, that sort of thing. Mark is concerned that these people do not understand the scientific background underpinning the strategies they may be quick to criticize. As we have seen with the group of non-scientists behind the effort to ban all geoengineering work out of fears of moral hazard and so forth, without regard for the real possibility that if we do not engage in some form of solar radiation management, there is little chance for our fragile civilization and ecosystems to survive the worsening onslaught of overheating induced extreme weather events. This fact escapes not only most social scientists, but also scientists in general who have not carefully looked into the issue of locked-in warming through a transdisciplinary lens. But it seems to be the group of social scientists who are most vocal in their protests and criticisms against geoengineering and SRM. So Mark is wondering if you would care to comment on this observation and on how we can be sure that concerns from people, quote, who do not really get the science of committed warming, end quote, and its implications for civilization will not overwhelm the practical voice of those scientists who can, as you can understand, that without some help from SRM, we are finished.
Yeah, okay, there's a lot to chew on there.
Yeah.
So I will address part of it. One is that I wouldn't want to necessarily paint with such a broad brush for the social sciences community. I've talked with quite a few social scientists. I think Holly Jean Buck might be one of the best people to read on this, who's a sociologist on loan to the Department of Energy now, but otherwise at University of Buffalo, I believe, SUNY Buffalo. So I think that one thing we should keep in mind is that decision-making about especially deployment, and I think also about certain forms of research and the allowability of especially outdoor testing shouldn't just be made by the physical sciences community, and it shouldn't just be made by the social sciences community. And I think importantly, it shouldn't just be made by the self-selected group of folks who hold PhDs in a disciplinary topic, because we know that we're weird. And by that, I mean both like Western educated, industrialized, rich democratic countries are the bulk of our community, but also we just systematically differ from the population at large. And if we're thinking about doing this for the benefit of all humanity, we actually need more perspectives in there, because we might have systematic and different sub-communities might have kind of systematic things that they think about a lot that might blind them to other issues, or that they might prioritize something more than other people would. So one way around that, I think we need a lot better public engagement and deliberation. So I think the kind of gold standard in this so far has been a study out of Arizona State University by Dan Sarowitz and colleagues, where they did a deliberative polling exercise. I think they had about 40 people in Arizona, about 40 people in Massachusetts, and people chosen, members of the lay public. They were given information about different types of climate interventions, about the physical science challenges, about some of the social science challenges, and then asked to do kind of like a series of exercises. So it's like a poll on steroids. That's why you can't get good sample sizes, because you had these 80 people there for I think like 2 days. So obviously it's only so much you can do of that. But you get really interesting results, and you kind of learn a little bit more about how the public would be thinking about this if they were given access to the best possible information. And I think that that gives us a lot of information to go off of what we should be thinking about. The other thing is that elected leaders, at least in democratic countries, are elected to lead. And what we know right now is the US Congress since 2020 has been specifically directing NOAA through its Earth's radiation budget program to specifically study the feasibility of some of these climate interventions. And if we're thinking about our solar climate interventions, if we're thinking about climate intervention more broadly, then you also have to bring in the Department of Energy's carbon removal, Earthshot, yeah, not Moonshot, Earthshot, and some of these other incentives we have now. So I'd say that I would be worried about giving any particular community too much decision-making power, especially one that is not necessarily accountable to any broader broader public. I think I've strayed a little bit from your from your question now, but yeah, in terms of that letter in particular, I think the best way to address it is to, where possible, address the concerns, but where not possible to, so like, I think like for us in terms of addressing this concern of lock-in, I think that it's not an unsurmountable problem. I think we actually can pre-identify certain areas that we would want to be looking out for. So like, I don't think that some of these governance challenges necessarily are the knockout blow that maybe other folks do. And I think the way to show that is to actually address them head on. But for other things, I think the best way to do it is to just, yeah, make the case to the public that this type of research is important. I would caution, I genuinely personally don't believe that the chances of, let's say, humanity going extinct from the levels of climate change we're on right now are particularly high, or and the way that climate change would do that would be more in terms of exacerbating other existential risks of a terrible pandemic maybe, or of great power conflict or something. There's some really interesting work from folks associated with the effective altruism community about thinking through under what circumstances climate change could lead to either human extinction or the collapse of civilization. And it's, I don't want to say impossible, but I'm personally, what keeps me up at night more is the unnecessary suffering that we could be seeing that we could avert. This could change. Maybe a couple things go wrong and we start getting back on a 6 degrees Celsius or higher trajectory. But at least right now, that's not, in my mind, that's not what I spend most of my time thinking about. I think more about the fact that we have the opportunity to potentially alleviate some unnecessary suffering, and we should be thinking really hard about whether or not we're able to do that.
Right, and how, yeah. Thank you. Okay, wonderful. Good to hear. And I think, well, we do have a few more questions if you have time to take a few more.
Yeah, I would be happy to.
Okay. So a question about how does increasing the number of cloud droplets impact infrared transmission? In other words, what is the relative impact of marine cloud brightening on the day cooling and night warming parts of the diurnal cycle?
Yeah, the infrared effect is pretty negligible, which is nice. So these clouds have, the cloud top temperature is very, very similar to that of the surface. So their greenhouse effect is relatively small. These are also, they tend to be optically thick in the infrared. So changing, yeah, you don't have as much leverage in the infrared as you do in the shortwave realm. I would need to maybe think about it a little bit in terms of downwelling long wave radiation at the surface and how you might care about that, but especially at top of atmosphere. And we've seen this like in, I'll go back to the Southeast Atlantic shipping corridor because I could pull the numbers off the top of my head more easily, but we found no statistically significant change in long wave top of atmosphere radiation, but a statistically significant and large change in the shortwave. So yeah, when you start getting into proposed interventions like cirrus cloud thinning, which I actually personally don't think should be considered a solar climate intervention because the solar side actually works in the wrong direction. If you start thinning cirrus clouds, you actually get more sunlight in the system, but you offset that from the increasing amount of infrared that you will let back out to space, because these cirrus clouds are really high in the atmosphere, which means they're really cold, which means they're really good at trapping radiation in the Earth's surface. So yeah, higher altitude clouds definitely have a bigger impact on the infrared. Part of the reason these low clouds are so nice is because their net cloud radio effect, as I kind of showed earlier, is dominated by that shortwave component. And we can, I don't want to say we can completely ignore the long wave component. We should still make sure we're looking at it, but it's not a big concern because of that.
Okay. Here's a question from Jonathan. nature provides many high-velocity climate change events. The Pinatubo eruption is a recent one. Massive injection of rapid cooling, then rapid fade-out and rapid reheating. Jonathan doesn't know of any observed termination shock effects from that. Do you know of any? And if not, does this imply we can put less concern on termination shock? You did mention something about that earlier.
Yeah, I think it suggests that we probably don't need to worry so much about termination shock at low levels. So I think that's what I said, or kind of what I was saying earlier, termination shock becomes an exponentially bigger problem the more forcing you do. So yeah, with a Pinatubo, you had sulfate that lasted in the stratosphere for 2 years and gradually fell out, and then you return to your previous climate. And we also know that we sometimes have really large El Nino events that have a temporary spike in warming, and we don't have catastrophic impacts from that. There are some big extreme weather impacts associated with El Nino, but that's more the actual dynamical driver of the Walker circulation El Nino in the Pacific, not necessarily from the global temperature response. So I think it does suggest that we don't need to weigh termination shock effects as highly if we're talking about going from a 2 degrees Celsius to a 1.5 degrees Celsius world. If you start talking about going from a 6 degrees Celsius world to a 2 degrees Celsius world, I would weigh that risk very, very highly. If you're talking about immediately unmasking 4 degrees Celsius of warming, there's no analog for that in the recent history.
Right. Okay, and maybe we'll just do one closing question, kind of general. This is from Bud. Is there any consideration of the same concept being applied to different topographical surfaces, for instance, land, mountains, deserts, farmland? You know, this is all about marine cloud brightening, but there's curiosity about land surfaces here to close with.
Yeah, someone from MIR could take over and talk about your work. Yeah, so there are proposals for, at the local scale, you could think of something like, if you have a city, you could potentially paint roofs white to make them more reflective and deal with them, at least locally, some of the urban heat island effects. One of the big ideas that MIR has been doing research on is looking at mirrors over land surfaces. We actually do know that, so we know this is at least theoretically possible. There actually has also been a climate cooling effect due to changing land use, which essentially is changing relatively dark forest lands for relatively bright grasslands and more desert surfaces. So potentially not the way you want to get a cooling effect, because we like those forests. They do very useful things for us. One thing over land is then you do have to start thinking about, yeah, like what are the cloud responses going to be? So if you do have more reflection over a certain land surface, are you going to get cloud responses that enhance that or offset that, et cetera? So it's not, yeah, it's not as simple as just taking the surface albedo and then figuring out what that would be at the top of the atmosphere. You do have to worry a little bit about how the atmosphere responds around it, but it's definitely something that has been looked at. But I personally haven't looked at it.
Mm-hmm, mm-hmm. Okay, well, thank you so much, Michael. There were a lot of questions, and I know there are a couple I didn't get to, but we really want to thank you for coming to MEERTALK today, for sharing your own expertise on marine cloud brightening. And it is crucial for the public to understand all of the research that's going on so we can address the increased heating on the planet. So thank you very much, and we are wishing you well in your further research, Michael.
Yeah, thank you so much for having me and for all of the really excellent questions. I very thoroughly enjoyed it.
Great. I want to announce to all of you that over the next few months, we're gathering names for anybody who's interested in trying to do your own community citizen science project, perhaps setting up reflectors. And you can, if you'd like to, you can email community@mirrorreflection.com. and let us know, your name and your city, your state or province, your country. People are beginning to write in, and we love hearing about projects that are, being experimented with. At MEER, we are trying to help educate the public while working toward a solution to the warming on the planet. So we invite you to keep learning and to keep coming back to MEERTALK. We are an almost all volunteer staff with only a few paid student researchers at the moment. So we'd like to encourage you to consider making a donation if you've enjoyed being here. You can also find our YouTube channel, MEER SRM, and our Twitter account as well, which is MEER SRM. Donations that you make help to fund materials and sensors for solar reflector field experiments, also basic expenses for researchers, and adaptation equipment going to communities that are already adversely affected by thermal heating. If you learned something from being here today, please do tell somebody you know about MEERTALK. And we hope to see you again next month on Sunday, September 4th, when Britt Ray will be presenting on the psychology of the climate crisis. So keep September 4th on your radar screen. And thank you everyone for coming. So good to see you.